Hello, this is Mrs. Scarple with the first part of topic 1.12. In this video, I'm going to introduce to you the transformations of functions, which you've likely seen before in previous classes when talking about transformations of parent functions. We're just going to be writing our transformations using function notation and being able to define a domain and range from the transformation and so on. So let's just start with what are the types of transformations we can see. Well, we've got vertical translations, and vertical means we're going to be moving our graph or our function up or down on our graph. You'll see the value of the transformation as being added or subtracted to an initial function. So what this function statement is saying here is that the function g of x is the function f of x plus a constant k. Because I'm adding a constant to the value of f of x, I'm adding that constant to the y value. So that's why we say this is a vertical translation. Now I do want to point out that there is an error in this graph in your notes packet. They didn't actually draw one of the segments correctly. So what it should look like, and I will draw this in red here, is if we're shifting everything down 2, because this is a -2, so that means we're going to have a vertical translation down 2 units. This point up here, if I shift down 2 units, would actually be on the x-axis. And then the end of that segment, the horizontal segment, would also be on the x-axis. So we're going to have it should have been drawn like this. I just wanted to point that out in case you're looking at it and you're like, but that doesn't really fit the down 2. So that's what happened there. There was a mistake in the way the graph was created. Horizontal translations are when we affect the value of the input. Now, notice that this is in parentheses. We describe the horizontal translation as being the opposite of h units. Now, I've had students in the past ask me, why do we use the opposite? Well, when you think about parent functions and how they're usually defined, they have a point at the origin, at 0, 0. So all of the translations are in regard to that 0, 0. So what I've told students in the past, if you see something like f of x plus 2, what would it take to turn this into a 0 so that we're going back to that initial parent function input at the origin? And it would be -2. So that's how I have described that. With horizontal, it is actually the opposite. So we are going to be moving left 2 in this case, and you can see that in this graph, that every point, its corresponding value, is shifted 2 units to the left. We also have vertical dilations. That happens in front of the function. And vertical dilations, we describe it as being the absolute value of A, so the amount of dilation is the absolute value. If you happen to see a negative, like we have here for g of x being -2 times f of x, the negative tells me that I'm going to reflect over the x-axis. So the negative tells me that I have a reflection. The 2 tells me that I have a dilation. So they're showing 2 things with this particular graph. So I can reflect this point right here, which is at 1, 2. When I reflect it, it would be down here at 1, -2. And I would take that y value times 2 and it would take me to -4. So I have the reflection and I have that stretch. For horizontal dilations, you'll see that inside the parentheses with the x. So hopefully you're seeing a pattern here. When it's vertical, it's going to be outside. When it's horizontal, it's going to be inside. Horizontal, the reciprocal of whatever that value is, whatever that coefficient is on the x, the reciprocal of it, that's why we have the 1 over b, becomes the factor. Now, we also have a negative on this one down here, so we don't really have a dilation happening. What we have instead is a reflection over the y-axis. Oops, I was going to write over and I wrote or instead, so over the y-axis. So let's just, this box here that's right below that table, anything that happens inside the parentheses is with the x variable. Whatever's happening with x is the opposite or the inverse of what it looks like. Anything that happens outside the parentheses is for y, and it does exactly like it looks. So the dilation will double. The translation will move up or down according to the sign, where with the x, the changes to x, if it's x plus 5, you're going to go left. If it's x minus 5, you're going to go right. If it's 3x, then we use the reciprocal of 3 as the dilation factor, so it's 1/3, and so on. So let's do a couple of examples. I'm going to start with example 2, and it's just a description. Let n be a function that is a transformation of the function m, such that n equals -4 times m of 2x. Describe the transformations of the function m that result with the function n. So I'm going to start with my x, and I see that I'm going to have a horizontal dilation with a factor of 2. Not 2, excuse me. It's horizontal, it's inside. I just finished saying it's the inverse when it's happening to x. It's a factor of 1/2. There we go. The negative tells me we're going to have a reflection over the x-axis. The 4 tells me that I'm going to have a vertical dilation with a factor of 4. Now you may recall using the words stretch and shrink. By using the word dilation, we don't have to necessarily worry about if it's stretching or if it's shrinking, if it's and what is happening. So if I say horizontal dilation with a factor of 1/2, that means it's going to become narrower because its distance is shrinking with that 1/2. If it's a vertical dilation with a factor of 4, it's actually going to get taller or longer vertically. Because we're multiplying those outputs by 4. The next one I want to look at is number 4. So this is going to be a combination of figuring out what is happening while also graphing its transformation. So we have the graph of y equals h of x has a hole at x equals 4. And we see that we have that hole But I also want you to see that we have this point that we're also going to have to move because it's part of the function. We have a discontinuity happening there. So the value when x is 4 is actually -1 and not the 2. And this graph consists of 3 linear segments. So we're going to sketch a graph of k on the same axes where k of x equals negative h of 2x plus 1. So I'm going to take that square off my graph so I don't get it confused with some of the things I'm doing. Let's just identify what we're having to do here. The negative in front tells me that I'm going to have a reflection over the x-axis. The 2 tells me that I'm going to have a horizontal, because it's inside the parentheses, a horizontal dilation with a factor of 1/2. And the plus 1 tells me that I'm going to have a vertical translation up 1 unit. So what I like to do when I'm doing these kinds of problems is pick specific points that are good points to see where change is happening so that I don't have to find too many different points. So these points that I'm circling are going to be excellent points to use for finding the transformed point for the function. So for the point, I'm just going to start with the one that has an x value of 0. Because it has an x value of 0, if I multiply that by 1/2, it isn't going to go anywhere. So I know that that is going to stay on the y-axis. If it reflects, then instead of being at -2, it's going to come up to +2, but then we have that translation up 1 unit, so that actually moves it up to 3 on the y-axis. I'm going to do the same thing here with the point -2, 1. So it's going to reflect down to -1. I'm going to multiply the x value by 1/2. So instead of -2, it'll be -1. And then I have to shift it up 1 unit. So that is at -1 on the y-axis. For the point at -4, -3, if I reflect it, it's at -4, +3. Multiply the -4 by 1/2. That takes me to -2. And then I move up 1 unit. This point on the far right is at 6, 4. So it would reflect at 6, -4. Multiply the x value by 1/2. So 1/2 of 6 is 3. And that shifts up 1 as well. Now I can't forget about the hole, so I should draw in a hole somewhere. So its reflection is currently at 4, 2. Its reflection would be at 4, -2. Multiply 4 by 1/2. That takes us to 2. And then we have to shift it up 1 unit. And I'm just going to draw a circle there because I know that's a hole. Now the point, the discontinuity from that, is at 4, -1. Its reflection would be at 4, 1. We multiply the horizontal value, the x value, by 1/2. So 4 times 1/2 is at 2. And we shift it up 1. And we have our point. So if I'm going to take my line tool here, and I'm going to connect my consecutive points. And yeah, that takes care of all of it. I just need to stretch the one segment if I can. There. So you'll see that it should still be a line here or look fairly close to a line. It's looking slightly off. I have this lower segment slightly off. But what you should notice is we have our original function has been flipped across the x-axis, but also squeezed together. So we still have that zigzag shape. We still have that point that is discontinuity from where the hole is at. But we have our transformation that fits the three requirements. And this concludes the video for the first part of topic 1.12.